Dear 4th grade students at the Department of Economics, this is our third recorded lecture for the econometrics module. I very much hope that you are all in the best of your states. Today we will continue covering a discussion of Chapter 5 of Gujarati 2004. From the previous chapters, you already know that hypothesis testing assumes that the model chosen for empirical analysis is adequate. This means that the model does not violate one or more assumptions underlying the classical normal linear regression model. So, tests of model adequacy should precede tests of hypothesis. Chapter 5 introduces only one test of model adequacy, that is the normality test, to find out whether the error term follows the normal distribution or not. In the previous lecture, we discussed the 5-step hypothesis testing procedure for the OLS regression coefficients. These steps are to be adapted to hypothesis testing involving the coefficient of determination testing and the normality assumption of the stochastic error term. The R-squared is a statistic that informs us how well the regression line fits the data points. In other words, it measures the fraction or the variance in the dependent variable that can be explained by the variability in the independent variable. If the regression line perfectly fits the data points, then R-squared equals 1, as we mentioned many times before in previous lecture. In contrast, if it equals to 0, then the model doesn't have any explanatory power in explaining variation in the dependent variable. In such a case, the regression line fits no better than the simple mean of the dependent variable. The test of the null hypothesis that R-squared equals 0 could thus be interpreted as a test of whether the regression explains anything at all. For a simple regression model, this test is equivalent to a test that the slope coefficient equals 0. Note that if a statistic is used to test whether R-squared is equal to 0 or not. For an OLS regression, if a statistic is computed as shown below, under the null hypothesis with normally distributed errors, the F statistic follows a F distribution with k minus 1 degrees of freedom for the numerator and n minus k degrees of freedom for the denominator. K is the number of the estimated coefficients including the intercept, whereas n is the sample size. Now let us consider some numerical examples to illustrate how to perform hypothesis testing involving R-squared. Before considering any numerical examples, let me remind you that we have to identify the decision rule related to hypothesis testing involving the coefficient of determination, as we have already done in the previous lecture for the OLS regression coefficients. As before, we are going to use both the critical value approach and the p-value approach. With regard to the first approach, if the computed F statistic is greater than its critical value obtained from the F table, then reject the null hypothesis. Alternatively, if the p-value computed for the F statistic is lower than the pre-specified level of significance, reject the null hypothesis. Recall our food expenditure regression model, which is shown by equations 3.6.1 and 3.6.2 in your textbook and in the previous lecture. Now we are going to employ the 5-step hypothesis testing procedure to show how well the regression model explains the variation in the consumption expenditure. Note that in the current example, we adopted the critical value approach for the decision rule step. Now, let us start our hypothesis testing procedure. In the first step, we state the null and alternative hypothesis. The null states that the coefficient of determination equals 0. This means that the model has no explanatory power in explaining the variation in the dependent variable, whereas the alternative hypothesis states that the null hypothesis is not true. In the second step, we determine the level of significance to be 5%. In the third step, we determine the test statistic to be F, as we mentioned earlier in the current presentation. It is computed according to the attached formula. In the fourth step, we have to decide when to reject the null hypothesis. To do so, we have to use the F table to obtain the critical value for F with 1 degree of freedom in the numerator and 8 degrees of freedom in the denominator for 5% of level of significance. This value equals 5.32. Note that this critical value is highlighted in the F table that is attached in the next slide. If the calculated F statistic is greater than its corresponding critical value, reject the null. Finally, in the last step, we make the decision. To make the decision, we have to compute the value of F statistic from our sample. As shown here, it equals 203. Now we compare this computed value by its corresponding critical value. Given that the F calculated is greater than its critical value, we reject the null hypothesis. Hence, the coefficient of determination is significantly different from 0. We could say that our model explains around 96% of variation in the weekly consumption expenditure. This indicates that the model fits the data points very well. From the attached F table, we pick the critical value at 5% level of significance and 1 degree of freedom in the numerator and 8 degrees of freedom in the denominator. This value, as mentioned earlier, equals 5.32. Here we are going to employ the p-value approach to perform the hypothesis testing involving R-square for quantifying the relationship between the expenditure in food and the total expenditure. As mentioned in the previous lectures, we employed cross-sectional data for a sample of 55 Indian households. Their data were collected in the year 1994. It is worth mentioning that the total expenditure is used as a proxy for income. Of interest to us is the bottom section of the screenshot shown in the previous lecture. Here, this bottom section is shown here in the current slides. This section provides the value of the coefficient of determination, the calculated F statistic, and its estimated p-value. The estimated p-value equals 0. Thus, at the first glance, we could say that the coefficient of determination is significantly different from the 0 beyond the 1% level of significance. Of course, here we adopt the same 5 steps as before, but I directly used the p-value approach to conclude the decision. So we could say that our model could explain around 36.9% of the variation of the food expenditure, which is quite good in the case of cross-sectional data. As mentioned earlier, tests of model adequacy should precede the tests of hypothesis. In the current presentation, we employ only one test of model adequacy, that is the normality test, to find out whether the error term follows the normal distribution. This is quite important because in small samples, the T, F, and chi-square tests require the normality assumption. Since in practice we don't observe the true error term, we use its proxy, the residual series. Fortunately, we could employ views to obtain the summary statistics of the residual series of a regression along with a histogram of their distribution. See the screenshot displayed here. The residuals from the food expenditure regression seem to be symmetrically distributed with normal tails. In other words, its skewness value is around 0. Moreover, the kurtosis value is very close to 3. However, let's identify the test statistic and the decision rule required to formally test for the normality assumption. The test statistic used to test for the normality assumption for the residuals is called Jarque-Pira statistic, or it is abbreviated here as JP statistic. To calculate this statistic, we need to know the values of the skewness and kurtosis of the residuals. For normally distributed variable, the skewness is 0 and the kurtosis is 3. So it's obvious from the Jarque-Pira statistic that if skewness equals 0 and kurtosis equals 3, its value is 0. Therefore, the closer is the value of Jarque-Pira statistic to 0, the better is the normality assumption. The Jarque-Pira statistic asymptotically follows a chi-square distribution with 2 degrees of freedom. Regarding the decision rule, as we already know, there are 2 approaches. The critical value approach tells us that if the calculated value of the Jarque-Pira statistic is greater than its corresponding critical value at the specified level of significance and degrees of freedom of 2, then reject the null hypothesis. If the p-value computed for the Jarque-Pira statistic is less than the level of significance, we have to reject the null hypothesis. Now we are going to employ the 5-step hypothesis testing procedure to test whether the residuals under consideration follow a normal distribution or not. First, let's state the null and alternative hypothesis. The null hypothesis states that residuals follow a normal distribution. In other words, the null hypothesis is a joint hypothesis that skewness equals 0 and kurtosis equals 3, versus the alternative hypothesis that residuals do not follow a normal distribution. We determine the level of significance at 5%. We identify the test statistic to be Jarque-Pira statistic, as we have just said. If the p-value calculated for the Jarque-Pira statistic is less than the level of significance, then reject the null hypothesis. Finally, let's make the decision whether to reject the null or not. The Jarque-Pira statistic is already computed by views. Its value is very close to 0. Given that the p-value is considerably larger than the level of significance, we couldn't reject the null hypothesis. Thus, the assumption of normality of the residuals seems to be appropriate in the current OLS regression. Now it's your turn to test whether the same residual series follow a normal distribution or not at 5% level of significance, but instead of using the p-value approach, you have to use the chi-square distribution table, which is attached here. So have fun. Answer the following questions in your textbook. Question 5.1 and question 5.3. Now we reach the end of our recorded lecture. Thank you.